Hello, welcome to this video on the null space. My name is Nakia. Remember, I'm happy to help you through this linear algebra journey. What is the null space? It's the set of solutions to the homogeneous equation AX equals 0. It's a set of equations, a system of equations, and we're looking for vectors that get mapped to 0 when multiplied by the matrix A. Before, when we saw it, we called it the kernel. Same thing, we just give it a different name now that we know about vector spaces, and we call it the null space. The 0 vector is always an answer to this solution. Any matrix times the 0 vector is going to equal to the 0 vector. So it's always a solution. We call that the trivial solution, and we're interested in non-trivial solutions. The dimension of the null space gets a special name. It's called the nullity of the matrix. So when you go to take the system and solve it, you'll be row reducing, but just to row echelon form. You don't have to go to reduced row echelon form. In the process of doing that, you'll be able to identify who are your free variables and which variables correspond to columns with leading ones. That'll be your separator, basically. And so the number of free variables is going to be exactly equal to the nullity of your matrix. Remember now, we're talking about the AX equals 0 homogeneous system of equations. And if the number of free variables is equal to 0, then we're going to say the nullity is equal to 0. I mean, that means that, you always have a solution. It is the trivial solution. AX equals 0 is always true for 0, but we don't want to say that the dimension is equal to 1 there. And so, therefore, what we say is that the dimension of the null space will be equal to 0 when x equals 0 has only the trivial solution. All right, great. Let's go look at an example. Our job, find a basis for the null space and the dimension of the null space, the nullity. Here's a 4x4 matrix. Doesn't have to be square when you do this. And you immediately go into the augmented homogeneous system, attach on a column of zeros, and we're going to row reduce this. We got to get the zeros underneath the 1. Thankfully, we have a 1 in the upper corner there. We do some row operation to get those zeros there. Once we do that, I want you to stop, take a look, and I want you to recognize something and do no further row operations. You see the repeated row 2 and row 3, exactly the same. With one operation, which you're not going to write, you can subtract one from the other and have a row of zeros. But then you see the bottom row, who is double, though, both the 2 and the 3. Row 2 and row 3. When you see that, that's another row of zeros. You can do an operation to get that row of zeros, but don't do it. Just recognize a row being a multiple of another row. Recognize when you have repeated rows. So we're going to have, in this case, 2 rows of zeros at the bottom. It doesn't always happen like that, but here we have it for this particular homogeneous system of equations, x equals 0. All right, I see 2 free variables. I got my leading ones on the diagonal, corresponding to, let's say, x1, x2, x3, x4. Every column corresponds to a variable, the coefficients on a variable. Let's call them with the subscripts x1, 2, 3, and 4. And so column 3 and 4, which go with x2 and go with x3 and x4, they're free variables. What we do there is we just pick some parameters and we let the parameters stand for those variables. So let's pick S for x3 and T for x4. The second row is an equation hidden in disguise involving x2, 3, and 4, but we know that x3 is S and x4 is T, so we can solve for x2. In the end, we want to get what x1 is in terms of S and T, what x2 is in terms of S and T, and we already know what x3 and 4 are, and that would be our answer there. And so let's go get x1 now from the first row. Knowing what we know about x2, 3, and 4, we can solve for x1, replace the S's and T's, and solve and simplify, and we'll have x1. Just collect this nicely in a vector, and then what you want to do is break that vector apart. You see we have exactly the vector that's there that was on the other slide, and now we're going to turn on one parameter, have it be 1, and turn off the other parameter and have it be 0. if S is 1 and T is 0, you'll have -1, 1, 1, 0. While the other way, if S is 0 and T is 1, you'll have -1, 2, 0, 1. Okay, you'll get skilled at that. You'll be able to do that without the off and on switches. But you see two vectors there, a linear combination of two vectors in your null space. Non-trivial vectors will come from this. You give me any S and T, and I'll come up with a vector who isn't all full of zeros that will be a solution to the homogeneous system. Our job, find the dimension of the null space and find a basis for the null space. So the number of vectors here will be the number of free variables. We could have answered that question earlier. We saw we had 2 free variables, then the nullity is 2. But then when we go through this process, we actually see these 2 vectors. We take these 2 vectors as the vectors that are in our basis. Any linear combination of these 2 vectors will give us a solution to the homogeneous system. They form the basis for the null space. All right, let's end this video now. Next video will be about the row space. The next video after that will be about the column space. The next video after that will be about connecting the column and the row space together. Also with the nullity and the null space, we'll put it all together with the rank nullity theorem. All right, take care. Thanks for watching.